Collapse of the wave function is one of the first things I learned in undergraduate quantum mechanics. The wave function is something that characterizes every quantum system, and it consists of a sum of terms for each possible result of a particular type of experiment that you can do on that system. Then we have coefficients like A, B, C that give you the probability of getting each outcome. Now, after the wave function is collapsed, if we repeat the same experiment, we get the same result over and over. Okay, as an example, suppose we get the result psi 2. Now psi equals psi 2. So there's only one possible result for the future experiments of the same type. Okay, so far, this is not so different from what we can do classically in measuring the polarization of light. Suppose these are two perfect polarizers, and they're linear. We take some unpolarized light, pass it through the first one, and then half of the light will come through, whichever angle it is. Half the light's going to come through the first one. Then if we put up another polarizer at the same orientation, then all of that light will come through. And we can use any number of polarizers, and then it doesn't change. So it's like the unpolarized light has collapsed to a polarization in this direction. What's different about quantum mechanics is that every system has a wave function. That includes a lot of things that we don't think of as having any kind of classical wave theory. It could be the energy level of an electron in an atom, or the spin of an electron. Now, different people describe this process in different ways. Some people say, no, the wave function doesn't collapse. Actually, the universe splits into different branches or parallel universes so that each possible result of the experiment does occur somewhere in the multiverse. There's another description in terms of pilot waves, which is more complicated, and it doesn't have a wave function collapse, but it gives the same results. Other people tell us there should be some kind of mechanism for collapse of the wave function in our universe. For example, Eugene Wigner, who won the Nobel Prize in Physics, suggested back in 1961 that conscious minds can collapse the wave functions when we do the experiment and make an observation. More recently, three scientists, Girardi, Rimini, Weber, known as GRW, said that there's a small probability per second of spontaneous collapse of the wave function for every particle in the universe. So for a body that has many particles, such as Schrodinger's cat, we'll never actually observe it to be in a superposition of states of alive and dead because it collapses to one or the other so quickly. Now, David Merman gave us a description of standard quantum mechanics as shut up and calculate. And what he was saying is that we just can't agree yet on what actually happens when we do an experiment. We can calculate the results, but we don't understand how we got there. The engineers say, who cares? We've got some great properties, in quantum systems that we can use to make products. So we're going to make some products out of this. To show you how it works, I want to focus on one paper that was done by Anton Zallinger and two of his colleagues. This was in 2001, so it's one of the early experiments. Zallinger was one of the three physicists who won the Nobel Prize in 2022 for work on entangled photons. Two other papers I want to mention that give us more details on entanglement swapping are given here. I like the title, that first one, Characterizing the Non-Local Correlations of Particles That Never Interacted. Because what we're going to see is that two particles that were formed in very different places can be entangled with each other, even though they have no history in common. We have two independent sources of entangled pairs of photons. One of them sends a photon to Alice and the other one to Bob, and then the other one sends a photon to Alice and then another photon to Victor. Okay, Alice has one photon from each of two different pairs of entangled particles. And what she does is perform a Bell state measurement. Now, to see what that means, the quantum computer folks define 4 different Bell states. Quantum computing is done with qubits. Each qubit can be 0 or 1. And when you have 2 qubits together, it's possible to write 4 entangled states. The physical embodiment of a qubit can be a lot of different things. It can be any quantum system with 2 different states. We're using polarization of the photon, so the 0 will correspond to a horizontal polarization, and the 1 will correspond to a vertical polarization. Those pluses and minuses represent the phase difference between the 2 photons. If they're perfectly in phase, you get a plus. If they're perfectly out of phase, you get a minus. Now, for what we're doing today, seeing how to collapse the wave function, the phase is not so important, so I'm going to focus on the horizontals and verticals. Okay, here's what the Bell states look like when we write them out in terms of horizontals and verticals. Now, for Alice's measurement, remember, you can pick any axis to measure a random polarization, and you get either vertical or horizontal along that axis. So what she's actually doing is measuring whether her 2 photons, which are completely independent, are closer to being both parallel or both perpendicular to each other. She's also measuring whether they're more in phase or out of phase. After she makes the measurement, they're exactly parallel or perpendicular, and exactly in phase or out of phase. She records the 4 Bell states, one of the 4 Bell states that she gets for each set of photons. Okay, so when she does the measurement, photon 1 collapses to being exactly horizontal and vertical, and photon 2 collapses to being exactly horizontal and vertical. So far, this is not very different from the classical measurements. But now we come to the quantum part. When Alice measures the polarization of photon 1, the system of particles, photon 0 and 1, this is the entangled pair, that collapses to a state where they both have the same polarization. So they're horizontal, horizontal, or vertical, vertical. So when she measures photon 1, then photon 0 is set. Also, when she measures photon 2, that collapses the state of photon 3 to being either horizontal or vertical to match photon 2. So now you see that photon 0 and photon 3 are either both horizontal or both vertical, or one horizontal and one vertical. And beyond that, these 2 are entangled. They have all the it's not just that they match, they have all the properties of entanglement that we've seen you've probably seen in previous videos, and they can do anything that the original pairs of entangled photons did. Okay, after that, Alice communicates her results to Victor. It's the which of those 4 Bell states she found. This is what keeps us from being able to use entanglement to communicate faster than light. Photon 0 and photon 3 become entangled instantaneously as far as we can tell from experiments. But Alice has to communicate with Victor by an ordinary means, like she can call him on the phone, she can send him an email, she can send him a letter, whatever. This is ordinary, slower than light communication. And this is necessary for Victor to do something with the entangled particles. But he can still do a lot. The final step in this experiment is that Bob is going to send photon 0 over to Victor. So now Victor has both photon 3 and photon 0, and he knows what kind of Bell state that they're in. So he can either use them for telecommunication purposes, or he can do a Bell test. So we want to just confirm that they're entangled. So he's going to do some Bell tests. He has to separate. First, we're going to repeat this whole thing many times. Then he separates his groups of photons as to which Bell state they were in, and then he can do the standard Bell test to determine whether they're entangled. Okay, if you're not familiar with Bell tests for entanglement, you can find a lot of videos, including one of mine. Over the last 20 years or so, since the paper by Salinger was published, there's been a ton of experiments and evidence collected in different labs to show that engineers really are collapsing the wave function. Whatever that means in a philosophical or physical sense, it works. This is useful in quantum computing, but it's only one step. So in future videos, I will try to explain more about what the engineers do with the quantum properties. Thank you for watching.